All right. So this is the problem. I came to it and I hadn't reviewed it, and it's a little bit tricky, and that's why I'm like, oh no. And then I didn't want to do math while all of you were telling me I wasn't good at math. Are you ready? Okay. So this is an ICE table. We have I'm just going to do it right here because there's not room under here. ICE. And I have this equation, which is the 2BrCl. I have Cl2 and Br2. Good so far? All right, here we go. So it didn't give me much. It gave me that it was 0.64, correct? And it said it did not contain any of these. That's a good sign that this is from an actual AP chemistry test, not one of mine, because they're very thorough. All right, so that means these are 0. All right, now the change we have, oh, I just realized I don't think I did that right. Anyway, so my numbers will be stupid. It won't matter a ton, but that was really dumb of me. Okay, whatever. I know my change for these is, well, I should just do it here. My change is a 2, right? So it's going to be negative 2x. Oh, I did it right. I did it right. I did it right.
So you have to do plus.
No one jump to the conclusions here, but you're right. But let's let me do this real quick. So that means this is plus just a single x, because this is half of that. We okay with that? There's one Cl2 to every 2 of those. And this is plus x, which I did it right. I'm an idiot. Okay, now at equilibrium, then I do know some things. I know this is equal to x, this is equal to x, and this is equal to 0.64 minus 2x. You with me so far? I don't know the change, so I just made a x. It could be a, could be whatever. And it's 2 of them because there's a 2 in front of this, and it's only a 1 because there's a 1 and a 1. Now they weren't written, but they would be there. Okay, so far sort of all right? Yeah. Okay, now I'm going to plug this into the expression. Kc is equal to the product, which is x and x, both raised to the first. Are you okay with that? Yeah. Can I write it as just x squared? Yeah. Okay, it's representing this x times this x, or x squared. That's where the x squared came from. In the denominator, I have 0.64 minus 2x, and it is, no, it is squared. Why squared? Because there's 2. And I missed that. Remember when I said, oh no, this is quadratic? If this is not a 2, then it is a quadratic, and it's a lot harder. But this one is not that bad. So we now have this function. We also actually do know the value of Kc. So 80 equals this. Now, if your denominator and your, numerator and denominator are both squared, you can get rid of the squares by square rooting the whole thing. Now, I have to square root both sides. Okay, now I'm coming down, and the square root of 80, Rollins was amazing. He was 1/100th off when I said, what's the square root of 80? He's like, probably like 8.94. It's 8.95. All right, so 8.95, that's the square root of 80. Oh no.
Yeah, I got 8.944.
Okay, well, he was right then. I just wrote 9.85. Okay, it's a 4, whatever. I did my math with a 5, so I'm going to keep the 5, and I apologize. All right, now that equals x now over 0.64 minus 2x. Are we okay with that?
Yeah.
Okay, then you have to multiply both sides by 0.64 minus 2x. Okay, so now I have x on the right side because these will cancel out, right? Then Rollins, help me with this real fast. So it's 5.72. That's what 0.64 times 8.9 is. And then what else did we have? Minus 17.9x. Okay, then how do I complete it from here?
You add the 17.9 to the egg.
So 5.72 equals 18.9x. I'll tell you what, there's a ton of kids on this planet that would put 17.9x squared. You do it. It offends me in every possible way, but you do it sometimes. All right, and then I just do what?
Divide by 18.9 on the side.
Just 0.3?
Oh, 0.303, yeah.
Sounds good to me. All right. So now what we come up here, this one works fine. X is 0.303. So this question says how many moles of Cl2 and Br? You would just double check there wasn't a number in front of your X, right? There is not. So the answer here would be 0.303. Yep. Okay, so I could, then I just plug in the whatever this is, and this is almost 0. Yes, Bennett. Not right now, but yeah, we can. So does it kind of make sense why I didn't want to do it in front of you? I'd forgotten. And when I looked at this in my head, pretty quickly, I was like, we're in trouble because I thought I was going to have x squared minus, it ends up to be 64 minus 200x. And like, you have to use the quadratic formula to figure that out. Now, we don't do that very often, so don't panic. Anyway, that's kind of the process for how you do it. You set up the ice table, you use a variable to represent your change, plug it in and pray, and 99% of the time, you'll have a square on the top and a square on the bottom. And if you can do that, then they're both in x's, and then x's talk to each other. Okay, we don't have a ton more. Le Chatelier's principle. All right, so we talked about the water example. You okay with that? Hold on. Yeah, not immediately, but I'm sure I'm pretty close to the end, I think, on this. Probably not. Oh, we're not that close to the end. Never mind. We're 2/3. Okay. Let me see here. No, we're right on. We're right on. I'm maybe a week behind, so. Usually I give a test on this before second try ends. But we're not that bad. All right, changing the concentration of a chemical. This is Le Chatelier's principle again. We'll shift the equilibrium to the side that would reduce the change in concentration. The chemical system will attempt to partially oppose the change effected to the original state of the equilibrium. In turn, the rate of reaction, extent, and yield of products will be altered corresponding to the impact of the system. That is word for word Le Chatelier's principle. It's super complicated, but if you, like I said before, if you remember, if you add, it wants to oppose that. So it moves to the other side you added from. If you take away, it wants to oppose that movement. So it fills back in. A really stupid but good example of that is two things. When you try and dig a hole in the sand, As soon as I scoop this sand out and throw it there, what's going to happen to that hole? Fills right in. The sand doesn't stack very well. So trying to dig a hole to China like I did as a kid in Vernal, I never got there. I just get to a certain angle and it would always fall back in because gravity made sand oppose my movements. Now, if you want to think about it the same way, if you try and make a pile of sand, get really tall, you add to the top and the sand just flows down the side, right?
Isn't it kind of like diffusion?
That's an interesting question. If you want to look at it that way, sure. Diffusion is not really related to the Chatelier's principle, but it's the same idea. If it's high, it wants to spread out. Gravity, yeah, and bones.
Or Dream says it broke it up.
Okay. Trying to fly. Oh, never mind. Yeah, when I was a kid, I put my Superman pillowcase, I tied it around my neck and jumped off my fence. Did I what? I did not fly. I felt the ground hit me really hard. Like a 4 foot. Oh, he rocked that test. I got an email that he got the highest of anyone that took it. Yeah. So
Well, he was studying for it for 3 days.
my boy, he doesn't work hard very often, but when he does, he works really hard. Oh, I just wanted to see how they were. Oh, the first was good. Okay, hey, random fact here. Whoever designed the pyramids in Egypt was smart. They built them at the same angle that sand naturally lies. So if they decayed over time, I assume that was what they planned. If they broke down over time, they would maintain pretty much the same shape and size.
You know how long it took people to figure out how they actually moved the rocks?
I don't know, but you sound angry about it. I'll tell you that right now. A long time.
I'm telling you,
Okay.
it was the aliens. There is no way those people built
Okay,
giant.
moving on. I'm going to talk. Feel free to ignore me. The transformation, the book loves the Haber process, and so does the AP chemistry test. The Haber process, because it's important. We wouldn't be here on the planet without it. All right, the Haber process was invented by, it's technically the Haber, it's from German. I don't remember his name. Let's just say Hans Haber. Is there anything I can say that won't distract you people? I don't think so either. That's where you take nitrogen and hydrogen and it makes ammonia. Ammonia is a substance that we put into the ground so that we can grow way more food than we typically should be able to. This is the basis of fertilizer. And without fertilizer, our planet would not sustain 7.9 billion people. So anyway, it's kind of important, but it's a really good way to study how the application of Le Chatelier's principle. So just go with me here. So here we have this example. Our H2, NH3, and N2 were at equilibrium right here. If you ever see in a graph the vertical, that's when we, as the scientists, add a chemical. The reaction didn't just suddenly increase by its own. We opened up the container and we injected more H2. Are you okay with that? If it's a curved line like this, that's the reaction reacting to my change. You with me? Okay, so we have N2 plus H2 goes to NH3, and it's a 2, and a 3. And that might be different than was up here. I don't remember the order, but it doesn't really matter. What I did, I opened the container and I injected H2. So I added H2. Look at the slope of this line. What am I doing? What is this reaction doing? It's decreasing. It's taking away, or it's opposing the change. All right, the H2, the reaction, I added H2, the reaction will always oppose my change. So even though it went up, it started to go down. Now remember, N2 is also a reactant. These are the two reactants. You with me? N2, it's just hanging out doing its own thing. But then suddenly we add H2 and then the N2 goes down. Well, why would it go down? Because we're making more products. If we make more NH3, that ties more N's and H2s together. And so my addition of H2 caused a decrease in both my reactants because I had an increase in products. If I add, that's what this picture is showing you. If I add, my equilibrium shifts towards the opposite side. Or if I add away, or if I add, I go away, sorry. If I add a concentration, the product, or sorry, oh my heavens, the reaction will move away from the side I added to. So if we came down here, oh, I always do that, whatever. If we come down here and this had a straight spike, we know it would come down like this, right? And reach a new equilibrium. What would happen to these things? All right, so it's the same as the H2. It would come down a little bit and the NH3 would go up, right? Okay, now, what if I add NH3? What's it going to do? It's going to go down and these things will come up a little bit. Whatever side I add, I always go to the other side. Yes, Grace.
So is that, like the lines that are going up and coming down, is it from the NH or the NH2 to the H2 creating the NH3? Like, where is the cut that coming from?
Where's the red line coming from?
Well, just all the changes in line. Is it since as NH3 increases, the other two are decreasing, so those are reacting to form more NH3?
Yes, correct. My reactants, instead of being separate now, they combine to make NH3. So the amount of NH3 went up, but each one of them, their concentrations went down. Okay. It's important that you can kind of picture this. In normal chemistry, I just teach kids and they memorize, add, weight, take, I stay. In AP, you got to memorize it and you got to understand it. You got to picture it. You got to know what a graph would look like. You have to explain it, like all of those things. All right, now, for the Haber process, temperature matters as well. So just kind of follow me here. This apparatus helps push the equilibrium to the right by removing the ammonia. Oh, never mind. This is not the temperature one yet. Okay, I'll come back to this in a second. If I am a producer of NH3, I don't want the system to ever reach equilibrium and stop producing NH3. Right? So the smartest thing I can do to always create products is to constantly remove products, because then H2 and N2 will try to react to make more of them. You with me? So if it makes sense if I put it in normal. If I want to make more bikes, I need to sell more bikes. Then there will be more demands. I assemble more parts, put them out, and they are sold. So when you make NH3, you have a device that happens. It causes the reaction to happen, and it's constantly removing NH3. If we're constantly removing NH3, then the equilibrium or the reaction will try to always fight that by making more NH3. It's kind of genius. So it's not hard though. Like life, it just makes sense. If we want to keep making stuff, well, we got to move the stuff. If I'm a bicycle maker and the warehouses that store them are all full, I'm going to stop making them. Or at minimum, I'm going to slow down. Yes.
What's like these? How do you keep the ammonia from like
going back? That's a good question. Some of it will. But they're going to keep it under the right conditions that we're going to learn, temperature and pressure, to try and keep it as much NH3 as possible.
So would manufacturing different chemicals is like the most important thing?
This is an extremely important thing. Most important thing, you'll see it when you enter, is safety. All right. Next is time, because this reaction is actually super slow. So they're going to sacrifice a little bit of yield for a lot of speed. But then the next is making sure that you have the equilibrium conditions correct. And this is on a test question. All right. In order to make this process happen, it needs to be done at certain temperatures. But those temperatures also make it so it's not super fast. So they're going to sacrifice some of the amount that they make so they can make it way faster. I don't know if that makes any sense, but it will hopefully as we go along. Okay, so whatever. Once we remove it, we pressurize it and make it a liquid. That's one of the main ways we keep it in H3. Okay, next up, temperature. And these are complicated. Don't try and write every single word, just follow along. The effect of changing the temperature in the equilibrium can be made clear by A, incorporating heat as either a reactant or product. So that's really important. We need to know where those things would go. Hopefully this is Jerry. Nope. Okay. Sorry, that was in my head. When you're given chemical equations, once again, you're AP, so it's not as easy. In regular chemistry, it's like A plus B goes to AB plus heat. On an AP test, you'll never get the word plus heat like this. That just doesn't happen. You will get a delta H value, or they'll tell you it's either exo or endo. And you need to remember, and you guys have been pretty good. We learned it in chapter 5, and most of the time you've been pretty good. A negative delta H means it's an exothermic process. All right. Oh my heavens. Exothermic. That means the heat is a product. If H is positive, that's endothermic. It means that the heat is a reactant. Exothermic are the things that come out. You good? All right. Things that exit are things on the right side. You need to go get a drink? Do you need Colin to punch you in the neck? Okay. All right. Sorry. That just came to mind. That's on video. Enjoy, world. Okay. B. All right. Well, let me know if he falls over. Letter B. Assuming that an increase in temperature increases the heat content of the system. So it's tricky. When we have A plus B goes to AB, when I add A, I'm just adding A. When I'm adding B, B, AB, AB. But when we talk about adding heat, this is all happening in a really awkward looking vessel here. All right. And the corks happen. It's right here. It's a closed vessel. And when I say I had heat, this whole thing is called the system. And I add heat to the system. I don't add heat to just one or the other. It's the whole thing. So that's what that is saying here for B. Assuming that an increase in temperature increases the heat content of the system. If I add temperature or add heat, all of it heats up. All right, letter C. Nope, never mind. When the reaction is exothermic, delta H is negative, puts out energy, heat is included as a product. I already said this. Hence, whenever increasing or decreasing the temperature would favor the forward or the reverse reaction can be determined by applying the same principles, the concentration changes. What? Just follow me here. For example, the reversible reaction of the Haber process, again, is as follows. It has a negative delta H, which would mean we would put heat as the product. And then what this is saying, as far as it is the same as concentration, if we add heat, I will move away from the heat term. If I remove heat, the system will go towards the heat term. So tell me something. When you're cold, what would you like to do? Get warm. Your body says, oh, my equilibrium is off. I am cold. I need heat. Whatever he said. So when I'm cold, I seek heat. A reaction is the same. When you remove heat, it wants to go towards the heat. It always opposes the change. So if you add heat, what's the fastest way to oppose that? Move away from the heat. So if you add heat, you go away. If you remove it, you stay. So it's the same saying. Add away, take, I stay. If I add heat, I go away. If I remove heat, I stay. Now, what do I mean once again by away? If I move away, that really means more of the side I move towards and less of the side I move away from. So if this were the graph, and I had my whatevers, okay, and I add heat, I would go towards the reactants. So they would come up a little bit and the product would go down. Take away heat, it's the exact opposite. Take away heat, I move towards the reactants or the heat term. So it would go up, sorry, products, not reactants. And these reactants would go down. All right. Having fun? Okay. Changes in pressure. It's going to be the same if you do it my way. Changes in pressure. Pressure will only affect an equilibrium with an unequal number of moles of reactants and products. Adios, friend. Okay, so look up here. It has to be an unequal number of moles of, and it has to be a gas, because pressure doesn't affect a liquid or a solid or aqueous. It only affects gases. Okay, so what we would do, the first thing to see if this change will even matter to the reaction is we add the moles of reactants. 3 plus 1 is 4. And then this only has 2. Now, be careful. If this said plus heat, would you count a 1 right here? No, that'd make me angry. All right. What?
Why would, like, has anyone done that?
Oh, I wouldn't bring it up if no one has. They do it all the time. They'll do it here too. It'll be plus, or it'll have delta H is a negative 36. And so they're like, oh, there's 38 over here. They're like, why, people? Why? Okay, but anyway. So the first question in pressure, are there unequal number of moles of products and reactants? Yes, there is. So pressure will matter. If you will do the following, it will work every single time. You with me? Add the moles, write them down, and always circle the bigger of the two numbers. Just do it because I tell you to. Always circle the bigger of the two numbers. And here's the reason why. If you circle the big number every time, if you add, you'll go away. If you take away, you stay. So follow my logic here. If this system's at equilibrium and I add pressure. So once again, this is in a sealed vessel. That's my cork. All right, here's my flask. Well, it's built weird. And I have all this stuff in here. If somehow I can like push a piston down on my microphone all of a sudden, and I increase the pressure on the inside of this. It's getting worse. All right. So I Increasing the pressure. This is making me. Where's the thing? I don't have one. Okay, increasing the pressure. I will always go away from the big number. Moles take up space. So 4 moles takes up twice the space that 2 moles take. So if I add pressure and I reduce the space, I will go to the side that requires less space. Does that sort of make sense? Now, if I loosen the pressure up, now there's more space, I'll shift towards the side with a bigger number. So if I always add, find the bigger number, circle it, add, I go away, remove, I stay. Now there's some complicated notes probably. Oh, there's not. Oh, good. Let me get rid of all these answers before we start some practice here. All right. Are we kind of all right with this? It's kind of tricky. Let's dive into these practice real quick and see. This is math. Did we already do this one? No, we did the 61, right? Oh, this is a good one. Try this one out real fast. And then Le Chatelier's principle. So number 6 here goes with what I just barely talked about. Try both these for a second. Nisha, you got me? All right. If this is 0.112 and this is double, oh, it's the reverse. Sorry, it's the reverse. So this would be around D. Is that right? All right. How do we figure out that it's D? All right. 1 over 0.112. The lesson learned here, that the Kp, Kc, or whatever the K is, we don't really care, of the reverse reaction is the reciprocal of it in the forward. All right, number 6 here, Le Chatelier's principle predicts that blank will result in an increase of the number of moles of SO3. So we're looking for whatever will cause the amount of products to go up. Now, I'll read these in a minute, but a couple things we could do is we could add SO2. We could add O2, or I know it seems weird, we can remove SO3. Does it say, oh, it does say it's exothermic, so I should say that, plus heat. So we could also remove heat. That would cause it as well, or cool it. Okay, increase the pressure. Oh, we got gases too. So I have too many things written in the way here. Whoops. So I have a 3 here, a 2 here, right? Circle. If I increase pressure, I go away from the big number, right? So A would work. There's no all the above, so is it just A, right? That's out. This is exo, so this would be heat. So increasing temperature would push it that way, so that's why that one's wrong. Removing oxygen, if I take away, I stay, so that's why that one's wrong. Increase the volume. Increase the volume is actually decreasing the pressure, so that would cause it to go to the 3, so it had to be A. We okay with A? Okay. Oh, come on. All right, we're trusting Caitlin, which usually goes pretty well. DMB.
No, it goes well.
All right, you guys are great. I'll see you tomorrow. I don't plan to teach